Have you ever wondered if time travel is possible? Can we really go back into the past or travel into the future? Let's dive into the captivating world of spaceship time machines. Have you ever gazed into a starry night, yearning to relive a moment from your past or to glimpse the wonders of the distant future? This age-old fascination with time travel has not only sparked our imaginations but also set the gears of scientific inquiry into motion. But is time travel confined to the world of fiction, or could it one day stand as a scientific reality? Time isn't merely a linear sequence of events we've grown accustomed to perceiving. It's a profound entity, deeply interwoven with the cosmos's fabric. Shaped and molded by various forces like gravity and velocity, time offers a mesmerizing dance of fluidity rather than a monotonous march. Now, let's talk about the possibility of time travel. Scientists have proposed various theories, such as wormholes and cosmic strings, that could serve as portals to different points in time. To understand the possibilities, we need to explore the concept of time itself. Time is a dimension, just like the three dimensions of space we're familiar with. It's the fourth dimension that governs our existence. The theory of relativity, proposed by Albert Einstein, suggests that time can be manipulated under certain circumstances. This brings us to the fascinating idea of time dilation. The 20th century bore witness to many scientific advances, but few were as profound or transformative as those introduced by the German-born physicist Albert Einstein. His groundbreaking ideas challenged long-standing beliefs and shook the very pillars upon which classical physics stood. Let's dive deep into this seismic shift in understanding, known as the Einsteinian revolution. The shift in perspective brought about by Einstein's groundbreaking theories, most notably his special and general theories of relativity, is known as the Einsteinian revolution. These theories tackled the nature of space, time, energy, and gravity, offering radical departures from the Newtonian physics that had dominated scientific thought for over 2 centuries. Einstein introduced the world to his special theory of relativity with the publication of his paper, On the Electrodynamics of Moving Bodies. Einstein's special theories of relativity included the following key principles. Regardless of the motion of its source or the observer, the speed of light in a vacuum is always constant at approximately 299,792,458 meters. Or 186,000 miles per second. Events that are simultaneous in one reference frame might not be simultaneous in another moving frame. Time can slow down or speed up depending on how fast you're moving compared to something else. Objects are measured to be shortened in the direction that they are moving with respect to the observer. Einstein's famous equation, E equals mc2, also emerged from this theory, suggesting that energy and mass are interchangeable, with c being the speed of light. A decade after his special theory, Einstein turned his attention to gravity. The general theory of relativity was a groundbreaking leap in understanding gravitational forces. Its primary insights include: rather than viewing gravity as a force between masses, as Newton did, Einstein posited that massive objects distort the spacetime around them, and other objects move along these distortions. This can be visualized as a bowling ball on a trampoline, causing nearby marbles to roll towards it. The theory led to many predictions, including the bending of light around massive objects, gravitational lensing, and time dilation near massive bodies. These predictions have since been experimentally confirmed, solidifying the theory's acceptance. Einstein's ideas weren't readily accepted by all, but as experiments and observations confirmed his predictions, the scientific community gradually embraced them. The implications were far-reaching. The seeds of quantum theory, which deals with the smallest scales of the universe, were also sown around this time. Although Einstein had reservations about quantum mechanics, his work laid some foundational ideas for this theory. Einstein's relativity played a pivotal role in understanding the universe's structure and the enigmatic entities called black holes. From the operation of GPS systems, which account for time dilation effects, to the understanding of nuclear reactions, Einstein's theories have had vast practical applications. In the vast and intricate tapestry of the cosmos, there exist theoretical entities that seem to be plucked straight from the pages of a science fiction novel. Among these, wormholes stand out as a particularly captivating concept. These speculative structures, often depicted as shortcuts across space and time, have tantalized physicists, mathematicians, and enthusiasts alike for decades. Let's journey deeper into the enigmatic world of wormholes. At its most basic, a wormhole, sometimes referred to as an Einstein-Rosen bridge, is a hypothetical tunnel-like structure that connects two separate points in space-time. If they exist, wormholes could potentially allow for faster-than-light travel between these points, circumventing the vast distances of regular space. Think of a wormhole as a type of subway tunnel, connecting two distant points in spacetime instantly. This is, in essence, the magic of a wormhole. Theoretical physics teases us with this fascinating concept, suggesting that spacetime shortcuts could indeed exist. However, as tantalizing as they sound, wormholes remain a formidable challenge. Their volatile and intense gravitational regions might make them impenetrable, crushing anything daring enough to venture within. The theoretical basis for wormholes comes from the equations of general relativity. In 1935, physicists Albert Einstein and Nathan Rosen used these equations to propose the existence of bridges through spacetime. Over the years, scientists have identified several potential types of wormholes. Traversable wormholes. These are the most commonly depicted in science fiction. They are stable, unchanging tunnels that can be used for travel in both directions. Einstein-Rosen bridges. These are connections between two black holes. However, they're believed to be highly unstable and would collapse quickly, making passage impossible. Theoretical physics proposes that to keep a wormhole open, it might require a type of exotic matter with negative energy. This matter counters the collapsing force and stabilizes the wormhole, though such matter is yet to be identified or proven to exist. The existence of wormholes could revolutionize our understanding of the universe and the possibilities of interstellar travel. However, there are several challenges. As mentioned, one of the significant issues with wormholes is their stability. Many are believed to close rapidly, preventing travel. Some theories suggest that naturally occurring wormholes, if they exist, might be microscopic in size, unsuitable for human or spacecraft travel. The necessity of exotic matter, which hasn't been proven to exist, is another substantial hurdle. If wormholes allow for travel back in time, they might introduce causality problems, like the famous grandfather paradox where a person might alter their own past, creating inconsistencies in the timeline. Within the expanse of the universe, light speed represents a cosmic speed limit, a barrier that nothing can surpass. Yet, as we approach this limit, the fabric of time itself begins to exhibit strange and counterintuitive behaviors. This phenomenon, known as time dilation, remains one of the most mind-bending implications of Einstein's theory of relativity. Time dilation occurs when an object or person moves at incredibly high speeds or near a massive source of gravity. In these extreme conditions, time slows down relative to the outside world. It's as if time operates on a different scale. Time dilation can be described as a difference in elapsed time as measured by two clocks due to a velocity difference between them or a difference in gravitational potential between their locations. Simply put, time can appear to move slower or faster depending on one's relative motion or position in a gravitational field. A classic thought experiment to explain this is the twin paradox. Imagine two twins, one stays on Earth, while the other embarks on a journey to a distant star and back, traveling at a significant fraction of light speed. Upon return, the traveling twin would be noticeably younger than the one who stayed on Earth. This isn't due to the rigors of space travel, but the genuine effects of time dilation. A clock positioned in a strong gravitational field, like closer to a planet, will tick slower than one in a weaker gravitational field, like farther away in space. This has been experimentally verified using precise atomic clocks placed on aircraft and compared to those on the ground. So back to our basic question, can we build a spaceship capable of time travel? The short answer is yes, at least on a subatomic level. The Large Hadron Collider built by the European Organization for Nuclear Research, CERN, routinely sends subatomic particles into the future by propelling protons at 99.999999% of the speed of light. But sending humans into the future at that rate is another matter. Given that subatomic particles can travel nearly the speed of light on a regular basis, conceptually, it should be simple for humans to accomplish the same feat. If you want to visit Earth in the year 3500, all it would take is to get on a spaceship and travel 99.995% the speed of light. Before we go out and build a near-speed light spaceship, we need to consider a couple of things. A human traveling in a spaceship approaching the speed of light would need 500 light-years to reach a destination in the year 3500. And let's not forget the return trip to Earth. It would take another 500 years to return home, so that's 1,000 years total. However, since they were moving so fast, the resulting time dilation wouldn't seem like 1,000 years for them since their internal clock has slowed. Their clock will be ticking at 1/100th of the rate of the clocks on Earth. They are only going to age about 10 years. While a millennium would pass for us on Earth, for them, it would be a decade. In practice, building a functioning time machine is currently beyond our technological capabilities. Building a time-traveling spaceship may be the best place to start, but the engineering and logistical challenges would be enormous. We are currently not even close to having a spaceship that can travel at the speed of light. The fastest spacecraft ever constructed is the Parker Solar Probe, which launched in 2018 with the mission to study the Sun's outer corona. It travels only 0.00067% the speed of light. A spaceship of this type would require an enormous amount of energy to propel it that fast. Scientists have suggested that an antimatter and fusion propulsion system could be the key to powering this type of spacecraft. A NASA report in 2010 indicated that a fusion-powered spacecraft could reach Jupiter in 4 months, creating the possibility that a manned exploration to our solar system and beyond could be within reach. Food on such a flight will also pose challenges. The ship would need to carry enough supplies, like food, water, and medicine, and be self-sufficient for the entire journey. Then there's the issue of spacecraft acceleration. In order to ensure that our astronauts would not be crushed by tremendous gravitational forces, the ship would need to provide gradual and steady acceleration as opposed to hitting a button and instantly accelerating the ship to the speed of light. Steady 1g acceleration similar to what is experienced on Earth would get the ship to approach velocities close to the speed of light, but it would also add to the length of the trip and limit how far in the future one could go. If we keep our distance at 500 light-years, using the 1g acceleration to near light speed scenario would increase the age of our astronauts by 24 years, so there are still some issues to work out. In addition, you would need material strong enough to tolerate the tremendous friction encountered when accelerating near the speed of light. To create a vehicle with these specifications would require a lot of time, resources, and money. Remember, time travel is still firmly in the realm of speculation and sci fiction. But it's our curiosity and exploration of possibilities that drive us forward as a species. So, the truth behind time machines remains a mystery. But that doesn't stop us from dreaming, questioning, and pushing boundaries. Thanks for watching. Remember to subscribe and hit that notification bell for more content.